getting a dataset. I'll see you there. Welcome back. So in the last video, we covered some of the fundamental computer vision libraries in PyTorch. The main one being Torch Vision, and then modules that stem off Torch Vision. And then of course, we've got torch_utils.data.dataset, which is the base dataset class for PyTorch, and data loader, which creates a Python iterable over a dataset. So let's begin where most machine learning projects do, and that is getting a dataset. Getting a dataset. I'm going to turn this into Markdown, and the dataset that we're going to be used to demonstrating some computer vision techniques is fashion MNIST, which is a take of the dataset we'll be using is fashion MNIST, which is a take on the original MNIST dataset, MNIST database, which is Modified National Institute of Standards and Technology database, which is kind of like the hello world in machine learning and computer vision, which is these are sample images from the MNIST test dataset, which are grayscale images of handwritten digits. So this, I believe, was originally used for trying to find out if you could use computer vision at a postal service to, I guess, recognize postcodes and whatnot. I may be wrong about that, but that's what I know. Yeah, 1998. So all the way back at 1998. How cool is that? So this was basically where convolutional neural networks were founded. I'll let you read up on the history of that. But neural networks started to get so good that this dataset was quite easy for them to do really well. And that's when Fashion MNIST came out. So this is a little bit harder. If we go into here, this is by Zalando Research, Fashion MNIST. And it's of grayscale images of pieces of clothing. So like we saw before, the input and the output, what we're going to be trying to do is turning these images of clothing into numbers and then training a computer vision model to recognize what the different styles of clothing are. And here's a dimensionality plot of all the different items of clothing, visualizing where similar items are grouped together. There's the shoes and whatnot. Is this interactive? Oh no, it's a video. Excuse me. There we go. To serious machine learning researchers. We're talking about replacing MNIST. MNIST is too easy. MNIST is overused. MNIST cannot represent modern CV tasks. So even now, Fashion MNIST, I would say, has also been pretty much solved, but it's a good way to get started. Now, where can we find such a dataset? We could download it from GitHub, but if we come back to the Torch Vision documentation, have a look at datasets, we have a whole bunch of built-in datasets. And remember, this is your extracurricular to read through these for 10 minutes or so each. But we have an example. We could download ImageNet if we want. We also have some base classes here for custom datasets. We'll see that later on. But if we scroll through, we have image classification datasets, Caltech 101. I don't even know what all of these are. There's a lot here. CFAR 100. So that's an example of 100 different items. So that would be a 100 class, multi-class classification problem. CFAR 10 is 10 classes. We have eMNIST. We have Fashion MNIST. Oh, that's the one we're after. But this is basically what you would do to download a dataset from torchvision.datasets. You would download the data in some way, shape, or form, and then you would turn it into a data loader. So ImageNet is one of the most popular, or is probably the gold standard dataset for computer vision evaluation. It's quite a big dataset. It's got millions of images, but that's the beauty of Torch Vision, is it allows us to download example datasets that we can practice on, or even perform research on from a built-in module. So let's now have a look at the Fashion MNIST dataset. How might we get this? So we've got some example code here. This is the documentation. Torchvision.datasets.fashionmnist. We have to pass in a route, so where we want to download the dataset. We also have to pass in whether we want the training version of the dataset or whether we want the testing version of the dataset. Do we want to download it? Yes or no? Should we transform the data in any way, shape, or form? So we're going to be downloading images through this function call or this class call. Do we want to transform those images in some way? What do we have to do to images before we can use them with a model? We have to turn them into a tensor, so we might look into that in a moment. And target transform is, do we want to transform the labels in any way, shape, or form? So often the datasets that you download from torchvision.datasets are pre-formatted in a way that they can be quite easily used with PyTorch, but that won't always be the case with your own custom datasets. However, what we're about to cover is just important to get an idea of what the computer vision workflow is, and then later on you can start to customize how you get your data in the right format to be used with the model. Then we have some different parameters here and whatnot. Let's just, rather than look at the documentation, if in doubt, code it out. So we'll be using Fashion MNIST, and we'll start by, I'm going to just put this here, from torchvision.datasets, and we'll put the link there, and we'll start by getting the training data. Set up training data. I'm trying to make some code cells here so that I can code in the middle of the screen. Set up training data. Training data equals datasets.fashionMNIST, because recall, we've already, from Torch Vision, we don't need to import this again, I'm just doing it for demonstration purposes, but from Torch Vision, import datasets, so we can just call datasets.fashionMNIST, and then we're going to type in root, see how the docstring comes up and tells us what's going on. I personally find this a bit hard to read in Google Colab, so if I'm looking up the documentation, I like to just go into here. But let's code it out. So root is going to be data, so where to download data to. We'll see what this does in a minute. Then we're going to go train. We want the training version of the dataset. So as I said, a lot of the datasets that you find in torchvision.datasets have been formatted into training dataset and testing dataset already. So this boolean tells us, do we want the training dataset? So if that was false, we would get the testing dataset of Fashion MNIST. Do we want to download it? Do we want to download? Yes, no. So yes, we do. We're going to set that to true. Now, what sort of transform do we want to do? So because we're going to be downloading images, and what do we have to do to our images to use them with a machine learning model? We have to convert them into tensors. So I'm going to pass the transform to tensor, but we could also just go torchvision.transforms.toTensor. That would be the exact same thing as what we just did before. And then the target transform, do we want to transform the labels? No, we don't. We're going to see how they come, or the targets, sorry. PyTorch is another way, another naming convention. Often uses target for the target that you're trying to predict. So using data to predict the target, which is I often use data to predict a label. They're the same thing. So how do we want to transform the data? And how do we want to transform the labels / targets? And then we're going to do the same for the test data. So we're going to go data sets. You might know what to do here. It's going to be the exact same code as above, except we're going to change one line. We want to store it in data. We want to download the training data set as false because we want the testing version. Do we want to download it? Yes, we do. Do we want to transform it, the data? Yes, we do. We want to use toTensor to convert our image data to tensors. And do we want to do a target transform? Well, no, we don't. We want to keep the label / the targets as they are. Let's see what happens when we run this. Downloading fashion MNIST. Beautiful. So this is going to download all the labels. What do we have? Train images, train labels, lovely. Test images, test labels, beautiful. So that's how quickly we can get a data set by using Torch Vision data sets. Now if we have a look over here, we have a data folder because we set the root to be data. Now if we look what's inside here, we have fashion MNIST, exactly what we wanted. Then we have the raw, and then we have a whole bunch of files here, which Torch Vision has converted into data sets for us. So let's get out of that. And this process would be much the same if we used almost any data set in here. Of course, they might be slightly different depending on what the documentation says and depending on what the data set is, but that is how easy Torch Vision datasets makes it to practice on example computer vision datasets. So let's go back. Let's check out some parameters or some attributes of our data. How many samples do we have? So we'll check the lengths. So we have 60,000 training examples and 10,000 testing examples. So what we're going to be doing is we're going to be building a computer vision model to find patterns in the training data and then use those patterns to predict on the test data. And so let's see a first training example. See the first training example. So we can just index on the train data. Let's get the 0th index, and then we're going to have a look at the image and the label. Oh my goodness, whole bunch of numbers. Now you see what the toTensor has done for us? So we downloaded some images, and thanks to this Torch Vision transforms toTensor. How would we find the documentation for this? Well, we could go and see what this does. Transforms toTensor. We can go to tensor. There we go. What does this do? Convert a pill image, so that's Python image library image, or NumPy array to a tensor. This transform does not support torch script, so converts a pill image or NumPy array, height, width, color channels in the range 0 to 255 to a torch float tensor of shape. See here? This is what I was talking about, how PyTorch defaults with a lot of transforms to CHW. So color channels first, height, then width, in the range of 0 to 1. So typically red, green, and blue values are between 0 and 255, but neural networks like things between 0 and 1. And in this case, it is now in the shape of color channels first, then height, then width. However, some other machine learning libraries prefer height, width, then color channels. Just keep that in mind. We're going to see this in practice later on. So we've got an image, we've got a label. Let's check out some more details about it. Remember how we discussed, oh, there's our label, by the way. So 9, we can go train data.classes, find some information about our class names. Class names. Beautiful. So number 9 would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this particular tensor seems to relate to an ankle boot. How would we find that out? Well, one second. I'm just going to show you one more thing. Class to IDX. Let's go train data.class to IDX. What does this give us? Class to IDX. This is going to give us a dictionary of different labels and their corresponding index. So if our machine learning model predicted 9 or class 9, we can convert that to ankle boot using this attribute of the train data. There are more attributes that you can have a look at if you like. You can go train data dot, and I just push tab to find out a bunch of different things. You can go data. There's the data. That'll be the images. And then I believe you can also go targets. So targets, that's all the labels, which is one big long tensor. Now let's check the shape. Check the shape of our image. So image.shape and label.shape. What are we going to get from that? Oh, label doesn't have a shape. Why is that? Well, because it's only an integer. So, oh, beautiful. Look at that. So our image shape is we have a color channel of 1. So let me print this out in something prettier. Print image shape, which is going to be image shape. Remember how I said it's very important to be aware of the input and output shapes of your models and your data? It's all part of becoming one with the data. So that is what our image shape is. And then if we go next, this is print image label, which is label, but we'll index on class names for label. And then we'll do that. Wonderful.
La felicità la trovi Sicuramente non all'università e non a studiare intelligenza artificiale. Per il resto non lo so. 52. Chi sei? Comunque mi sono dimenticato di una cosa, di mettere il link del video che sto guardando per dare credito a questo creatore qui. Oh, scusate, proprio. Questo è il link del video del ragazzo che sta facendo il tutorial.
So our image shape is currently in the format of color channels height width. We've got a bunch of different numbers that's representing our image. It's black and white. It only has one color channel. Why do you think it only has one color channel? Well, because it's black and white. So if we jump back into the keynote, fashion we've already discussed this. Grayscale images have one color channel. So that means that for black, the pixel value is 0, and for white, it's some value for whatever color is going on here. So if it's a very high number, say it's 1, it's going to be pure white. If it's like 0.001, it might be a faint white pixel. But if it's exactly 0, it's going to be black. So color images have 3 color channels for red, green, and blue. Grayscale have 1 color channel. But I think we've done enough of visualizing our images as numbers. How about in the next video, we visualize our image as an image? I'll see you there. Welcome back. So in the last video, we checked the input-output shapes of our data, and we downloaded the Fashion MNIST dataset, which is comprised of images, or grayscale images of t-shirts, trousers, pullovers, dress, coat, sandal, shirt, sneaker, bag, ankle boot. Now, we want to see if we can build a computer vision model to decipher what's going on in Fashion MNIST, so to separate, to classify different items of clothing based on their numerical representation. And part of becoming one with the data is, of course, checking the input-output shapes of it. So this is the Fashion MNIST dataset from Zalando Research. Now, if you recall, why do we look at our input and output shapes? Well, this is what we looked at before. We have 28 by 28 grayscale images that we want to represent as a tensor. We want to use them as input into a machine learning algorithm, typically a computer vision algorithm, such as a CNN. Then we want to have some sort of outputs that are formatted in the ideal shape that we'd like. So in our case, we have 10 different types of clothing. So we're going to have an output shape of 10. But our input shape is what? So by default, PyTorch turns tensors into color channels first. So we have an input shape of none, 1, 28, 28. So none is going to be our batch size, which of course we can set that to whatever we'd like. And so our input shape format is in NCHW, or in other words, color channels first. But just remember, if you're working with some other machine learning libraries, you may want to use color channels last. So let's have a look at where that might be the case. We're going to visualize our images. So I'll make a little heading here, 1.2. Now this is all part of becoming one with the data. In other words, understanding its input and output shapes, how many samples there are, what they look like, visualize, visualize, visualize. Let's import matplotlib. I'm just going to add a few code cells here. Import matplotlib.pyplot, pyplot as PLT. Now, let's create our image and label, is our train data 0, and we're going to print the image shape so we can understand what inputs are going into our matplotlib function. And then we're going to go plot.imshow, and we're going to pass in our image and see what happens. Because recall, what does our image look like? Image. Our image is this big tensor of numbers. And we've got image shape, 128, 128. Now, what happens if we call plot.imshow? What happens there? Oh, we get an error. Invalid shape, 128, 128 for image data. Now, as I said, this is one of the most common errors in machine learning is a shape issue. So the shape of your input tensor doesn't match the expected shape of that tensor. So this is one of those scenarios where our data format, so color channels first, doesn't match up with what matplotlib is expecting. So matplotlib expects either just height and width, so no color channel for grayscale images, or it also expects the color channels to be last. So we'll see that later on, but for grayscale, we can get rid of that extra dimension by passing in image.squeeze. So do you recall what squeeze does? It's going to remove that singular dimension. If we have a look at what goes on now, beautiful, we get an ankle boot. Well, that's a very pixelated ankle boot, but we're only dealing with 28 by 28 pixels, so not a very high definition image. Let's add the title to it. We're going to add in the label. Beautiful. So we've got the number 9 here. So where if we go up to here, that's an ankle boot. Now let's plot this in grayscale. How might we do that? We can do the same thing. We can go plot plt.imshow. We're going to pass in image.squeeze. And we're going to change the color map. CMap equals gray. So in matplotlib, if you ever have to change the colors of your plot, you want to look into the CMap property or parameter, or sometimes it's also shortened to just C. But in this case, imshow is CMap. And we want to plot title. And we're going to put in class names and the label integer here. So we have a look at it now. We have an ankle boot, and we can remove the axes too if we wanted to. Plot.axis and turn that off. That's going to remove the axis. So there we go. That's the type of images that we're dealing with. But that's only a singular image. How about we harness the power of randomness and have a look at some random images from our data set. So how would we do this? Let's go plot more images. We'll set a random seed. So you and I are both looking at as similar as possible images, 42. Now we'll create a plot by calling plot.figure, and we're going to give it a size. We might create a 9 by 9 grid. So we want to see 9 random images from our data set. So rows, cols, or sorry, maybe we'll do 4 by 4. That'll give us 16. We're going to go for I in range, and we're going to go 1 to rows times columns plus 1. So we can print I. What's that going to give us? We want to see 16 images, or thereabouts. So 16 random images, but used with a manual seed of 42 of our data set. This is one of my favorite things to do with any type of data set that I'm looking at, whether it be text, image, audio, doesn't matter. I like to randomly have a look at a whole bunch of samples at the start so that I can become one with the data. With that being said, let's use this loop to grab some random indexes. We can do so using Torch's rand_int, so random integer, between 0 and length of the training data. This is going to give us a random integer in the range of 0 and however many training samples we have, which in our case is what? 60,000 or thereabouts. So we want to create the size of 1, and we want to get the item from that so that we have a random index. What is this going to give us? Oh, excuse me, maybe we print that out. There we go. So we have random images. Now, because we're using manual seed, it will give us the same numbers every time. So we have 37542, 37542. And then if we just comment out the random seed, we'll get different numbers every time. But this is just to demonstrate. We'll keep the manual seed there for now. You can comment that out if you want different numbers or different images, different indexes each time. So we'll create the image and the label by indexing on the training data at the random index that we're generating. And then we'll create our plot. So fig, or we'll add a subplot. Fig add subplot. And we're going to go rows, cols, I. So at the ith index, we're going to add a subplot. Remember, we set rows and columns up to here. And then we're going to go plt.inShow. We're going to show what? We're going to show our image, but we have to squeeze it to get rid of that singular dimension as a color channel. Otherwise, we end up with an issue with map.lib. We're going to use a color map of gray so it looks like the image we plotted above. And then for our title, it's going to be our class names indexed with our label. And then we don't want the axes because that's going to clutter up. Our plot. Let's see what this looks like. Oh my goodness, look at that. It worked first go. Usually visualizations take a fair bit of trial and error. So we have ankle boots, we have shirts, we have bags, we have ankle boots, sandal, shirt, pullover. Oh, do you notice something about the data set right now? Pullover and shirt. To me, they look quite similar. Do you think that will cause an issue later on when our model is trying to predict between a pullover and a shirt? How about if we look at some more images? We'll get rid of the random seed so we can have a look at different styles. So we have a sandal, ankle boot, coat, t-shirt, top, shirt. Oh, is that a little bit confusing that we have a class for t-shirt and top and shirt? Like, I'm not sure about you, but what's the difference between a t-shirt and a shirt? This is just something to keep in mind. As a t-shirt and top, does that look like it could be maybe even a dress? Like the shape is there? So this is just something to keep in mind going forward. Chances are, if we get confused on our, like you and I looking at our data set, if we get confused about different samples and what they're labeled with, our model might get confused later on. So let's have a look at one more and then we'll go into the next video. So we have sneaker, trouser, shirt, sandal, dress, pullover, bag, t-shirt. Well, that's quite a difficult one. Doesn't look like there's even much going on in that image. But the whole premise of building a machine learning model to do this would be, could you write a program that would take in the shapes of these images and write a rule-based program that would go, hey, if it looks like a rectangle with a buckle in the middle, it's probably a bag. I mean, you probably could after a while, but I prefer to write machine learning algorithms to figure out patterns in data. So let's start moving towards that. We're now going to go on figuring out how we can prepare this data to be loaded into a model. I'll see you there. All right. So we've got 60,000 images of clothing that we'd like to build a computer vision model to classify into 10 different classes. And now that we've visualized a fair few of these samples, do you think that we could model these with just linear lines, so straight lines? Or do you think we'll need a model with nonlinearity? So I'm going to write that down. So do you think these items of clothing, images, could be modeled with pure linear lines? Or do you think we'll need nonlinearity? Don't have to answer that now. We can test that out later on. You might want to skip ahead and try to build a model yourself with linear lines or nonlinearities. We've covered linear lines and nonlinearities before, but let's now start to prepare our data even further to prepare data loader. So right now, our data is in the form of PyTorch datasets. So let's have a look at it. Train data. There we go. So we have dataset, which is of fashion MNIST. And then if we go test data, we see a similar thing, except we have a different number of data points. We have the same transform on each, we turn them into tensors. So we want to convert them from a dataset, which is a collection of all of our data, into a data loader. Recall that a data loader turns our dataset into a Python iterable. So I'm going to turn this into Markdown. Beautiful. More specifically, can I spell right? It doesn't really matter, we want to just code right. I'm not here to learn spelling. We want to turn our data into batches, or mini batches. Why would we do this? Well, we may get away with it by building a model to look at all 60,000 samples of our current dataset, because it's quite small. It's only comprised of images of 28 by 28 pixels. And when I say quite small, yes, 60,000 images is actually quite small for a deep learning scale dataset. Modern datasets could be in the millions of images. But if our computer hardware was able to look at 60,000 samples of 28 by 28 at one time, it would need a fair bit of memory. So we have RAM space up here, we have GPU memory, we have compute memory, but chances are that it might not be able to store millions of images in memory. So what you do is you break a dataset from, say, 60,000 into groups of batches or mini batches. So we've seen batch size before. Why would we do this? Well, one, it is more computationally efficient, as in your computing hardware may not be able to store in memory at 60,000 images in one hit. So we break it down to 32 images at a time. This would be batch size of 32. Now, again, 32 is a number that you can change. 32 is just a common batch size that you'll see with many beginner-style problems. As you go on, you'll see different batch sizes. This is just to exemplify the concept of mini batches, which is very common in deep learning. And why else would we do this? The second point, or the second main point, is it gives our neural network more chances to update its gradients per epoch. So what I mean by this will make more sense when we write a training loop, but if we were to just look at 60,000 images at one time, we would, per epoch, so per iteration through the data, we would only get one update per epoch across our entire data set. Whereas if we look at 32 images at a time, our neural network updates its internal states, its weights, every 32 images, thanks to the optimizer. This will make a lot more sense once we write our training loop. But these are two of the main reasons for turning our data into mini batches in the form of a data loader. Now, if you'd like to learn more about the theory behind this, I'd highly recommend looking up Andrew Ong mini batches. There's a great lecture on that. So yeah, large-scale machine learning, mini batch gradient descent, mini batch gradient descent. Yeah, that's what it's called, mini batch gradient descent. If you look up some results on that, you'll find a whole bunch of stuff. I might just link this one. I'm going to pause that. I'm going to link this in there. So for more on mini batches, see here. Now, to see this visually, I've got a slide prepared for this. So this is what we're going to be working towards. This is our input and output shapes. We want to create batch size of 32 across all of our 60,000 training images. We're actually going to do the same for our testing images, but we only have 10,000 testing images. So this is what our dataset is going to look like batched. So we're going to write some code, namely using the data loader from torch.utils.data. We're going to pass it a dataset, which is our trained data. We're going to give it a batch size, which we can define as whatever we want. For us, we're going to use 32 to begin with. And we're going to set shuffle equals true if we're using the training data. Why would we set shuffle equals true? Well, in case our dataset for some reason has order, say we had all the pants images in a row, we had all the t-shirt images in a row, we had all the sandal images in a row. We don't want our neural network to necessarily remember the order of our data. We just want it to remember individual patterns between different classes. So we shuffle up the data, we mix it up. And then it looks something like this. So we might have batch number 0, and then we have 32 samples. Now, I ran out of space when I was creating these, but we got, that was fun, up to 32. So this is setting batch size equals 32. So we look at 32 samples per batch. We mix all the samples up, and we go batch, and we'll have however many batches we have, we'll have number of samples divided by the batch size. So 60,000 divided by 32, what's that, 1,800 or something like that? So this is what we're going to be working towards. I did want to write some code in this video, but I think to save it getting too long, we're going to write this code in the next video. If you would like to give this a go on your own, here's most of the code we have to do. So there's the train data loader. Do the same for the test data loader. And I'll see you in the next video, and we're going to batchify our fashion MNIST dataset. Welcome back. In the last video, we had a brief overview of the concept of mini batches. And so rather than our computer looking at 60,000 images in one hit, we break things down. We turn it into batches of 32. Again, the batch size will vary depending on what problem you're working on, but 32 is quite a good value to start with and try out. And we do this for two main reasons. We jump back to the code. Why would we do this? It is more computationally efficient. So if we have a GPU with, say, 10 gigabytes of memory, it might not be able to store all 60,000 images in one hit. In our dataset, because it's quite small, it may be able to, but it's better practice for later on to turn things into mini batches. And it also gives our neural network more chances to update its gradients per epoch, which will make a lot more sense once we write our training loop. But for now, we've spoken enough about the theory. Let's write some code to do so. So I'm going to import data loader from torch.utils.data, import data loader. And this principle, by the way, preparing a data loader, goes the same for not only images, but for text, for audio, whatever sort of data you're working with. Mini batches will follow you along, or batches of data will follow you along throughout a lot of different deep learning problems. So set up the batch size hyperparameter. Remember, a hyperparameter is a value that you can set yourself. So batch size equals 32, and it's practice. You might see it typed as capitals. You won't always see it, but you'll see it quite often, a hyperparameter typed as capitals. And then we're going to turn datasets into iterables, so batches. So we're going to create a train data loader here of our fashion MNIST dataset. We're going to use data loader. We're going to see what the doc string is. Or actually, let's look at the documentation. Torch data loader. This is some extra curriculum for you too, by the way, is to read this data page, torchutils.data, because no matter what problem you're going with deep learning or PyTorch, you're going to be working with data. So spend 10 minutes just reading through here. I think I might have already assigned this, but this is just so important that it's worth going through again. Read through all of this. Even if you don't understand all of what's going on, it helps you know where to look for certain things. So what does it take? Data loader takes a data set. We need to set the batch size to something. It's the default of 1. That means that we would create a batch of 1 image at a time in our case. Do we want to shuffle it? Do we want to use a specific sampler? There's a few more things going on. Number of workers. Number of workers stands for how many cores on our machine do we want to use to load data. Generally, the higher the better for this one. But we're going to keep most of these as the default because most of them are set to pretty good values to begin with. I'll let you read more into the other parameters here. We're going to focus on the first 3. Dataset, batch size, and shuffle, true or false. Let's see what we can do. So dataset equals our train data, which is 60,000 fashion MNIST. And then we have a batch size, which we're going to set to our batch size hyperparameter. So we're going to have a batch size of 32. And then finally, do we want to shuffle the training data? Yes, we do. And then we're going to do the same thing for the test data loader, except we're not going to shuffle the test data. Now, you can shuffle the test data if you want, but in my practice, it's actually easier to evaluate different models when the test data isn't shuffled. So you shuffle the training data to remove order until your model doesn't learn order. But for evaluation purposes, it's generally good to have your test data in the same order because our model will never actually see the test data set during training. We're just using it for evaluation. So the order doesn't really matter to the test data loader. It's just easier if we don't shuffle it because then if we evaluate it multiple times, it's not being shuffled every single time. So let's run that. And then we're going to check it out, our train data loader and our test data loader. Beautiful. We've got instances of torchutils data loader. And now let's check out what we've created, eh? I always like to print different attributes of whatever we make. Check out what we've created. This is all part of becoming one with the data. So print f, I'm going to go data loaders and then pass in. This is just going to output basically the exact same as what we've got above. Test data loader. And we can also see what attributes we can get from each of these by going train data loader. I don't need caps lock there. Train data loader, full stop, and then we can go tab. We've got a whole bunch of different attributes. We've got a batch size. We've got our data set. We want to drop the last, as in if our batch size overlapped with our 60,000 samples, do we want to get rid of the last batch? Say, for example, the last batch only had 10 samples. Do we want to just drop that? Do you want to pin the memory? That's going to help later on if we wanted to load our data faster. A whole bunch of different stuff here. If you'd like to research more, you can find all the stuff about what's going on here in the documentation. But let's just keep pushing forward. What else do we want to know? So let's find the length of the train data loader. We'll go length, train data loader. So this is going to tell us how many batches there are. Batches of, which of course is batch size. And we want print length of test data loader. We want length test data loader batches of batch size. So let's find out some information. What do we have? Oh, there we go. So just we're seeing what we saw before with this one. But this is more interesting here. Length of train data loader. Yeah, we have about 1,875 batches of 32. So if we do 60,000 training samples divided by 32, yeah, it comes out to 1875. And if we did the same with 10,000 for testing samples of 32, it comes out at 313. This gets rounded up. So this is what I meant, that the last batch will have maybe not 32 because 32 doesn't divide evenly into 10,000. But that's okay. And so this means that our model is going to look at 1,875 individual batches of 32 images rather than just one big batch of 60,000 images. Now, of course, the number of batches we have will change if we change the batch size. So we have 469 batches of 128. And if we reduce this down to 1, what do we get? We have a batch per sample. So 60,000 batches of 1, 10,000 batches of 1. We're going to stick with 32. But now let's visualize. So we've got them in train data loader. How would we visualize a batch or a single image from a batch? So let's show a sample. I'll show you how you can interact with a data loader. We're going to use randomness as well. So we'll set a manual seed and I'm going to get a random index. Random IDX equals torch rand int. We're going to go from 0 to length of train features batch. Oh, where did I get that from? Excuse me, getting ahead of myself here. I want to check out what's inside the training data loader. We'll check out what's inside the training data loader because the test data loader is going to be similar. So we want the train features batch. So I say features as in the images themselves, and the train labels batch is going to be the labels of our dataset or the targets in PyTorch terminology. So next iter data loader. So because our data loader has 1,875 batches of 32, we're going to turn it into an iterable with iter, and we're going to get the next batch with next. And then we can go here, train features batch.shape, and we'll get train labels batch.shape. What do you think this is going to give us? Well, there we go. Look at that. So we have a tensor. Each batch we have 32 samples. So this is batch size, and this is color channels, and this is height, and this is width. And then we have 32 labels associated with the 32 samples. Now, where have we seen this before? If we go back through our keynote, input and output shapes. So we have shape equals 32, 28, 28, 1. So this is color channels last, but ours is currently in color channels first. Now, again, I sound like a broken record here, but these will vary depending on the problem you're working with. If we had larger images, what would change? Well, the height and width dimensions would change. If we had color images, the color dimension would change. But the premise is still the same. We're turning our data into batches so that we can pass that to a model. Let's come back. Let's keep going with our visualization. So we want to visualize one of the random samples from a batch, and then we're going to go to go image label equals train features batch, and we're going to get the random IDX from that, and we'll get the train labels batch, and we'll get the random IDX from that. So we're matching up on the, we've got one batch here, train features batch, train labels batch, and we're just getting the image and the label at a random index within that batch. So, oh, excuse me, I need to set this equal there. And then we're going to go plt.imShow. What are we going to show? We're going to show the image, but we're going to have to squeeze it to remove that singular dimension. And then we'll set the CMAP equal to grade. And then we'll go plt.title. We'll set the title, which is going to be the class names indexed by the label integer. And then we can turn off the accesses. You can use off here, or you can use false. Depends on what you'd like to use. Let's print out the image size, because you can never know enough about your data. And then print. Let's also get the label, and label shape, or label size. Our label will be just a single integer, so it might not have a shape. But that's okay, let's have a look. Oh, a bag. See, look, that's quite hard to understand. I wouldn't be able to detect that that's a bag. Can you tell me that you could write a program to understand that? That just looks like a warped rectangle to me. But if we had a look at another one, we'll get another random, oh, we've got a random seed, so it's going to produce the same image each time. So we have a shirt, okay, shirt. So we see the image size there, 128, 28. Now, recall that the image size it's a single image, so it doesn't have a batch dimension. So this is just color channels, height, width. We'll go again. Label 4, which is a coat. And we could keep doing this to become more and more familiar with our data. But these are all from this particular batch that we created here. Coat. And we'll do one more, another coat. We'll do one more just to make sure it's not a coat. There we go, we got a bag. Beautiful. So we've now turned our data into data loaders. So we could use these to pass them into a model. But we don't have a model. So I think it's time in the next video, we start to build model 0. We start to build a baseline. I'll see you in the next video. Welcome back. So in the last video, we got our data sets, or our data set into data loaders. So now we have 1,875 batches of 32 images for the training data set, rather than 60,000 in one big data set. And we have 313 batches of 32 for the test data set. Then we learned how to visualize it from a batch, and we saw that we have still the same image size, one color channel, 28, 28. All we've done is we've turned them into batches so that we can pass them to our model. And speaking of model, let's have a look at our workflow. Where are we up to? Well, we've got our data ready. We've turned it into tensors through a combination of torch vision transforms, torch utils data.dataset. We didn't have to use that one because torch vision.datasets did it for us with the fashion MNIST dataset. But we did use that one. We did torch utils.data, the data loader, to turn our data sets into data loaders. Now we're up to building or picking a pre-trained model to suit your problem. So let's start simply. Let's build a baseline model. And this is very exciting because we're going to build our first model, our first computer vision model. Albeit a baseline, but that's an important step. So I'm just going to write down here. When starting to build a series of machine learning modeling experiments, it's best practice to start with a baseline model. I'm going to turn this into Markdown. A baseline model. So a baseline model is a simple model you will try and improve upon with subsequent models/experiments. So you start simply, in other words, start simply and add complexity when necessary. Because neural networks are pretty powerful, right? And so they have a tendency to almost do too well on our data set. That's a concept known as overfitting, which we'll cover a little bit more later. But we build a simple model to begin with, a baseline. And then our whole goal will be to run experiments according to the workflow, improve through experimentation. Again, this is just a guide. It's not set in stone, but this is the general pattern of how things go. Get data ready, build a model, fit the model, evaluate, improve the model. So the first model that we build is generally a baseline. And then later on, we want to improve through experimentation. So let's start building a baseline. But I'm going to introduce to you a new layer that we haven't seen before. And that is creating a flatten layer. Now, what is a flatten layer? Well, this is best seen when we code it out. So let's create a flatten model, which is just going to be nn.flatten. And where could we find the documentation for this? We go nn flatten. Flatten in PyTorch. What does it do? Flattens a contiguous range of DIMs into a tensor for use with sequential. So there's an example there, but I'd rather, if in doubt, code it out. So we'll create the flatten layer, and of course, all nn.flatten or nn.modules could be used as a model on their own. So we're going to get a single sample. So x equals train features batch. Let's get the first one, 0. What does this look like? So it's a tensor. X. Maybe we get the shape of it as well. X shape. What do we get? There we go. So that's the shape of x. Keep that in mind when we pass it through the flatten layer. Do you have an inkling of what flatten might do? So our shape to begin with is what? 128, 28. Now let's flatten the sample. So output equals, we're going to pass it to the flatten model, x. So this is going to perform the forward pass internally on the flatten layer. So perform forward pass. Now let's print out what happened. Print out what happened. Print shape before flattening equals x.shape. And we're going to print shape after flattening equals output.shape. So we're just taking the output of the flatten model and printing its shape here. Oh, do you notice what happened? Well, we've gone from 128.28 to 1,784. Wow, what does the output look like? Output. Oh, the values are now in all one big vector. And if we squeeze that, we can remove the extra dimension. So we've got one big vector of values. Now, where did this number come from? Well, if we take this, and this is, what shape is it? We've got color channels, we've got height, we've got width. And now we flattened it to be color channels, height, width. So we've got one big feature vector because 28 by 28 equals what? We've got one value per pixel, 784. One value per pixel in our output vector. Now, where did we see this before? If we go back to our keynote, if we have a look at Tesla's, takes 8 cameras, and then it turns it into a 3-dimensional vector space. Vector space. So that's what we're trying to do here. We're trying to encode whatever data we're working with. In Tesla's case, they have 8 cameras. Now theirs has more dimensions than ours because they have the time aspect because they're dealing with video and they have multiple different camera angles. We're just dealing with a single image here. But regardless, the concept is the same. We're trying to condense information down into a single vector space. And so if we come back to here, why might we do this? Well, it's because we're going to build a baseline model and we're going to use a linear layer as the baseline model. And the linear layer can't handle multi-dimensional data like this. We want it to have a single vector as input. Now this will make a lot more sense after we've coded up our model. So let's do that. From torch, import nn. We're going to go class, fashion, mnist, model v0. We're going to inherit from nn.module. And inside here, we're going to have in the init function, in the constructor, we're going to pass in self. We're going to have an input shape, which we'll use a type hint, which will take an integer. Because remember, input shape is very important for machine learning models. We're going to define a number of hidden units, which will also be an integer. And then we're going to define our output shape, which will be, what do you think our output shape will be? How many classes are we dealing with? We're dealing with 10 different classes, so our output shape will be, I'll save that for later on. I'll let you guess for now, or you might already know. We're going to initialize it. And then we're going to create our layer stack. Self.layerStack equals nn.sequential. We'll call that sequential. Whatever you put inside sequential, if data goes through sequential, it's going to go through it layer by layer. So let's create our first layer, which is going to be nn.flatten. So that means anything that comes into this first layer, what's going to happen to it? It's going to flatten its external dimensions here. So it's going to flatten these into something like this. So we're going to flatten it first, flatten our data. And then we're going to pass in our linear layer. And we're going to have how many in features? This is going to be input shape, because we're going to define our input shape here. And then we're going to go out features equals hidden units. And then we're going to create another linear layer here. And we're going to set up in features equals hidden units. Why are we doing this? And then out features equals output shape. Why are we putting the same out features here as the in features here? Well, because subsequent layers, the input of this layer here, its input shape has to line up with the output shape of this layer here. Hence why we use out features as hidden units for the output of this nn.linear layer. And then we use in features as hidden units for the input value of this hidden layer here. So let's keep going. Let's go def, we'll create the forward pass here, because if we subclass nn.module, we have to override the forward method. The forward method is going to define what? It's going to define the forward computation of our model. So we're just going to return self.layerStack of x. So our model is going to take some input, x, which could be here, x. In our case, it's going to be a batch at a time. And that's going to pass each sample through the flatten layer. It's going to pass the output of the flatten layer to this first linear layer. Then it's going to pass the output of this linear layer to this linear layer. So that's it. Our model is just two linear layers with a flatten layer. The flatten layer has no learnable parameters. Only these two do. And we have no nonlinearities. So do you think this will work? Does our dataset need nonlinearities? Well, we can find out once we feed our model to the data. But let's set up an instance of our model. So torch.manual seed. Let's go set up model with input parameters. So we have model 0 equals fashion mness model, which is just the same class that we wrote above. And here's where we're going to define the input shape equals 784. Where did I get that from? Well, that's here. That's 28 by 28. So the output of flatten needs to be the input shape here. So we could put 28 by 28 there, or we're just going to put 784 and then write a comment here. This is 28 by 28. Now, if we go, I wonder if nn.linear will tell us. and n.linear will tell us what it expects as in features. Size of each input sample, shape, where star means any number of dimensions including none, in features, linear weight. Well, let's figure it out. Let's see what happens. If in doubt, code it out, hey? We'll see what we can do. Hidden units equals, let's go with 10 to begin with. How many units in the hidden layer? And then the output shape is going to be what? Output shape is length of class names, which will be 1 for every class. Beautiful. And now let's go model 0. We're going to keep it on the CPU to begin with. We could write device agnostic code, but to begin, we're going to send it to the CPU. I might just put that up here, actually, to CPU. And then let's have a look at model 0. Wonderful. So we can try and do a dummy forward pass and see what happens. So let's create dummy x equals torch rand. We'll create it as the same size of image, just a singular image. So this is going to be a batch of 1, color channel 1, height 28, height 28. And we're going to go model 0 and pass through dummy x. So this is going to send dummy x through the forward method. Let's see what happens. Okay, wonderful. So we get an output of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 logits. Beautiful. That's exactly what we want. So we have one logit value per class that we have. Now, what would happen if we got rid of flatten? And then we ran this, ran this, ran this. What do we get? Oh, mat1 and mat2 two shapes cannot be multiplied. So we have 28 by 28 and 7. Okay, what happens if we change our input shape to 28? We're getting shape mismatches here. What happens here? Oh, okay, we get an interesting output. But this is still not the right shape, is it? So that's where the flatten layer comes in. What is the shape of this? Oh, we get 1, 1, 28, 10. Oh, so that's why we put in flatten, so that it combines it into a vector. So we get rid of this. See if we just leave it in this shape, we get 28 different samples of 10, which is not what we want. We want to compress our image into a singular vector and pass it in. So let's reinstantiate the flatten layer, and let's make sure we've got the right input shape here, 28 by 28. And let's pass it through. Torch size 110. That's exactly what we want, one logit per class. So this can be a bit fiddly when you first start, but it's also a lot of fun once you get it to work. And so just keep that in mind. I showed you what it looks like when you have an error. One of the biggest errors that you're going to face in machine learning is different tensor shape mismatches. So just keep in mind the data that you're working with, and then have a look at the documentation for what input shape certain layers expect. So with that being said, I think it's now time that we start moving towards training our model. I'll see you in the next video. Welcome back. In the last video, we created model 0, which is going to be our baseline model for our computer vision problem of detecting different types of clothing in 28 by 28 grayscale images. And we also learned the concept of making sure, or we rehashed on the concept of making sure our input and output shapes line up with where they need to be. We also did a dummy forward pass with some dummy data. This is a great way to troubleshoot to see if your model shapes are correct, if they come out correctly, and if the inputs are lining up with where they need to be. And just to rehash on what our model is going to be, or what's inside our model, if we check model 0 state dict, what we see here is that our first layer has a weight tensor. It also has a bias, and our next layer has a weight tensor, and it also has a bias. So these are, of course, initialized with random values, but the whole premise of deep learning machine learning is to pass data through our model and use our optimizer to update these random values to better represent the features in our data. And I keep saying features, but I just want to rehash on that before we move on to the next thing. Feature in data could be almost anything. So for example, the feature of this bag could be that it's got a rounded handle at the top. It has an edge over here, it has an edge over there. Now, we aren't going to tell our model what features to learn about the data. The whole premise of it is to, well, the whole fun, the whole magic behind machine learning is that it figures out what features to learn. And so that is what the weights and bias matrices or tensors will represent, is different features in our images. And there could be many because we have 60,000 images of 10 classes. So let's keep pushing forward. It's now time to set up a loss function and an optimizer. Speaking of optimizers, so 3.1, set up loss, optimizer, and evaluation metrics. Now, recall in Notebook 2, I'm going to turn this into Markdown, we created, oh, I don't need an emoji there. So this is, by the way, we're just moving through this workflow. We've got our data ready into tensors. We've built a baseline model. It's now time to pick a loss function and an optimizer. So if we go back to Google Chrome, let's write here, loss function. What's our loss function going to be? Since we're working with multi-class data, our loss function will be nn.cross entropy loss, and our optimizer. We've got a few options here with the optimizer, but we've had practice in the past with SGD, which stands for stochastic gradient descent, and the atom optimizer. So our optimizer, let's just stick with SGD, which is kind of the entry-level optimizer, torch optim SGD for stochastic gradient descent. And finally, our evaluation metric. Since we're working on a classification problem, let's use accuracy as our evaluation metric. So recall that accuracy is a classification evaluation metric. Now, where can we find this? Well, if we go into learnpytorch.io, this is the beauty of having online reference material. In here, neural network classification with PyTorch. In this notebook, section 02, we created, do we have different classification methods? Yes, we did. So we've got a whole bunch of different options here for classification evaluation metrics. We've got accuracy, precision, recall, F1 score, a confusion matrix. Now we have some code that we could use. If we wanted to use torch metrics for accuracy, we could. And torch metrics is a beautiful library that has a lot of evaluation. Oh, it doesn't exist. What happened to torch metrics? Maybe I need to fix that link. Torch metrics has a whole bunch of different PyTorch metrics. So very useful library. But we also coded a function in here, which is accuracy FM. So we could copy this straight into our notebook here. Or I've also, if we go to the PyTorch Deep Learning GitHub, I'll just bring it over here. I've also put it in helperfunctions.py. Now this is a script of common functions that we've used throughout the course, including if we find accuracy function here. Calculate accuracy. Now, how would we get this helper functions file, this Python file, into our notebook? One way is to just copy the code itself straight here, but let's import it as a Python script. So import request, then we're going to go from pathlib import path. So we want to download. And this is actually what you're going to see very common practice in larger Python projects, especially deep learning and machine learning projects, is different functionality split up in different Python files. And that way you don't have to keep rewriting the same code over and over again. Like, you know how we've written a training and testing loop a fair few times? Well, if we've written it once and it works, we might want to save that to a .py file so we can import it later on. But let's now write some code to import this helperfunctions.py file into our notebook here. So download helper functions from learn PyTorch repo. So we're going to check if our helper functions.py, if this already exists, we don't want to download it. So we'll print helper functions.py already exists, skipping download, and we're going to go else here. If it doesn't exist, so we're going to download it, downloading helperfunctions.py, and we're going to create a request here with the request library equals requests.get. Now, here's where we have to pass in the URL of this file. It's not this URL here. When dealing with GitHub, to get the actual URL to the files, many files, you have to click the raw button. So I'll just go back and show you. Click raw here, and we're going to copy this raw URL. See how it's just text here? This is what we want to download into our Colab notebook. And we're going to write it in there, request equals request.get, and we're going to go with open, and here's where we're going to save our helperfunctions.py. We're going to write binary as file, F is for file. We're going to go f.write request.content. So what this is saying is Python is going to create a file called helperfunctions.py and give it write binary permissions as F is for file, short for file. And then we're going to say f.write, hey, request, get that information from helperfunctions.py here, and write your content to this file here. So let's give that a shot. Beautiful. So downloading helperfunctions.py, let's have a look in here. Do we have helperfunctions.py? Yes, we do. Wonderful. So now we can import our accuracy function. Where is it? There we go. Import accuracy function. So this is very common practice when writing lots of Python code, is to put helper functions into .py scripts. So let's import the accuracy metric. Accuracy metric from helper functions. Of course, we could have used torch metrics as well. That's another perfectly valid option, but I just thought I'd show you what it's like to import your own helper function script. Of course, you can customize helper functions apply to have whatever you want in there. So see this, we've got from helper functions, import accuracy function. What's this saying? Could not be resolved. Is this going to work? It did. And where you can go accuracy function, do we